Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, in our last class we have studied about few of the properties of colloids. Some of the properties we have already seen even in the previous class, the class before the last class. And so some properties then we saw in the last class, and this is what we have seen, that all the colloidal particles carry certain charges. These charges may be positive or negative in nature. So what do we see, that if a solution or the dispersed phase, this dispersion medium contains a particular type of, suppose it contains many an electrolyte, so it may be having two different charges. So the charge which is common, or the ion which is common to the ion that is already there in the colloidal particle, gets absorbed. So the ion which is common to the colloidal particles only gets absorbed by the colloidal particles, and so we see a different charge will appear on the colloidal particle. For example, suppose an AgI colloidal particles has to be formed. Silver iodide colloidal particles, so AgI, suppose it is being precipitated during the formation of the colloid, and this AgI, and suppose in that solution the dispersion medium, the ion that is in excess is potassium iodide, then this fall this particles, colloidal particle AgI will absorb iodide ions. It will not absorb K plus ions. However, if suppose AgI precipitate is formed and if the solution contains AgNO3 in excess, silver nitrate in excess, in that case, the ion, which is what ion is the common, AgI contains two ions, Ag and I, and so the solution contains AgNO3, so it will absorb Ag plus ions, and so it will become positively charged. And if it absorbs iodide ions, it will become negatively charged, and this is how the charge gets generated on the colloidal particles. Some other mechanisms are also there that we have seen. Then we show the electrical double layer formation on the colloidal particles. So what we have seen, colloidal particles, they already carry certain charges because of the absorption of certain ions. And once the absorption of certain ions, so these ions are become electrically charged, and also the colloidal solution contains some electrolytes as well. So it will, these colloidal particles will attract cations immediate to it, and this cation, it forms a fixed layer or the external layer, and so on. Later on, what we see, the diffused layer is also being formed, and what we have seen, the diffused layer is slightly bigger, so the net charge we see at the end of the diffused layer is zero. So the potential at the end of the diffused layer becomes zero. However, the potential at the surface of colloidal particle is maximum. This potential means the magnitude of the potential, which may be positive or negative. And what we also see, there is certain, after the colloidal particles up to a certain distance, even the solution dispersion medium and even the charges, they moves along with the colloidal particles. As we know, colloidal particles are in continuous random motion into the colloidal solution, and that with the motion that we call Brownian motion. So the boundary of this layer, which is fixed and which moves with the colloidal particles or the solid particles, is called a slipping plane, this boundary, and the potential at the slipping plane is called the zeta potential, and the potential at the fixed layer or the stern layer is called stern potential, and the zeta potential is actually very responsible for the stability of the colloidal particles. And here you can see this charge, if this colloidal particle is having negative charge, so zeta potential, this you can see negative potential in this case. Then we show other electrical properties of colloids as well, that in the form of electrophoresis. And electrophoresis is the experiment which is used to find out the nature of charge on the colloidal particles. So we use a U-shaped tube, and on this U-shaped tube, two platinum electrodes are suspended, and these electrodes are actually given the opposite polarities. Because of that, the electric field will be generated, and because of this opposite polarity, one is behaving as anode and another behaves as cathode. And so if the colloidal particle moves towards the anode, means the positive electrode, it means it is negatively charged, and if the colloidal particle moves towards the cathode, means that towards the negative electrode, it means it is positively charged. And this is how we find out the charge on the colloidal particles. Then what we see, by certain means, if you stop the movement of this colloidal particles under the electric field, then what we see, the dispersion medium moves, it shifts towards, and that movement of the dispersion medium is termed electroosmosis. What we know in osmosis, only the solvent phase moves towards through an semi-permeable membrane, and so here the solvent phase is dispersion medium. So dispersion medium, movement of dispersion medium under electric field when solved, movement of solved particles is prohibited by certain means is called electroosmosis. Then we show coagulation or the precipitation of the colloidal particles, and what we know, as we know, the colloidal particles, they carry certain charge. If by certain means, if we to destroy that charge or if we remove that charge, what we see, the colloidal particles, they get settled, they get precipitated, and this process is called coagulation or flocculation or precipitation of the sol or the colloidal particle. And this coagulation of lyophilic salts, then we have seen different methods for the coagulation of lyophilic salts. Means what are the methods that one can use for the coagulation or precipitation of lyophilic salts? And if you know those methods, means those regions which cause the which causes the precipitation of lyophilic salts, and then we can be very careful so that these condensations may not appear during the experiments if you want the colloidal particles to be stable for a longer duration of time. So, means colloidal solution to be stable. So, examples that these methods for the coagulation of the lyophilic salts are, means the by electrophoresis one can do by mixing two oppositely charged salts as well. The precipitation of colloids occurs, and this process is called mutual coagulation. Means if you are mixing two oppositely charged salts, then the coagulation of each salts occurs, and this process is called mutual coagulation. Then by boiling also one can coagulate or precipitate the colloidal solution. By persistent dialysis, these things we have seen, I have explained this earlier. Then by adding electrolyte and shown. Then we show this. So the ion responsible for neutralization of charge on the particle is called coagulating ion. A negative ion causes precipitation of positively charged sol and vice versa. These things we have seen. Then we show Hardy-Suzy rule. So Hardy-Suzy rule actually describes, so the greater the valency of a positively charged ion of the electrolyte added to a colloidal solution, the faster is the coagulation of the colloidal solution. What we have seen, so the colloidal solution, if in the colloidal solution, if you add electrolyte, colloidal solution, the diffused layer gets destroyed. So then, and because of the dis, destruction of the diffused layer, colloidal particles they get precipitated, so charge gets removed, and so what we see, they get precipitated, and this precipitation happens because the colloidal electrolyte contains both positive and negative charged ions. So if the colloid is positively charged ion, so then the precipitation occurs because of the negative charge of the colloid. And if the colloid is negatively charged, then the precipitation occurs because of the positively charged ions of the electrolyte. And that is what we have to see in the Hardy-Suzy rule. The greater the valency of the oppositely charged ion on the electrolyte, and if the, and this coagulation depends on the valency of the charge or the valency on the of the that cation or the anion, means the oppositely charged ion, means how much charge the cationic positive charge or negative charge, means the cationic charge or anionic charge is there on the ion. Depending on the charge is more or the valence that we call the valency is more, the coagulation power of that particular electrolyte will be more. So the greater the valency of oppositely charged ion of the electrolyte added to a colloidal solution, the faster is the coagulation of colloidal solution. This is known as Hardy-Suzy rule. And for example, if a colloid is negatively charged, for example, arsenic sulfide, we know usually all the sulfides are negatively charged salts. So salt is negatively charged. Then the cation of the electrolyte will cause the coagulation of this salt. And the cations, suppose there are many electrolytes which contains different cations. For suppose this aluminum, one of the electrolyte contains aluminum 3 plus ions, another contains barium 2 plus ions, and another contains sodium 1 plus ion. So the coagulation power of the different electrolytes will be in this order. The electrolyte containing aluminum 3 plus ion will have the highest coagulation power than the barium containing electrolyte than the sodium containing electrolyte, because this ion is having highest valency, aluminum ion is having highest valency. And similarly, if the colloidal solution is positively charged, as the example we have already seen, usually metal hydroxides forms positively charged colloids. So the example is FeOH thrice, ferric hydroxide. And then in this case, the negative ion of the electrolyte will cause the coagulation of this cation, and the coagulating power of different electrolytes containing different anions will be in this order. This is the ferrocyanide. Ferrocyanide means iron is in +2 oxidation state. If iron is in +3 oxidation state, means this charge on this ion is 3 minus, then iron will be in +3 oxidation state, then that ion is called ferricyanide. So this one is ferrocyanide, which has 4 negative charge, so its valency is highest. Then the phosphate ion, which valency is 3, means that it is 3 negative charge on it, then sulfate ion and the chloride ion. So the coagulation power will, or the coagulating power will follow this order of all these different electrolytes. Let us now see coagulation or flocculation values. The minimum concentration of an electrolyte in a millimolar per liter required to cause precipitation of a sol in 2 hours is called coagulation value of the electrolyte. So what is the coagulation value or the flocculation value of an electrolyte? So it's the minimum concentration of an electrolyte, and that too in the unit millimoles per liter. So millimoles per liter that is required for the coagulation of sol in 2 hours. The duration that is given is 2 hours is called coagulation value of the electrolyte. The smaller the quantity needed, the higher the coagulating power of an ion will be. And this is what we know, it is a very common sense thing. So if the smaller quantity of a particular electrolyte is required, it means its coagulation power is more. It means even in a smaller concentration, it can coagulate a particular sol or a particular colloid. It means there is coagulating power of this electrolyte is more. It means very small amount of this electrolyte is required for the coagulation of a given sol in just 2 hours. So thus a smaller coagulation of flocculation value indicates the greater coagulating power of the electrolyte. So coagulation power or the coagulating power is inversely proportional to the coagulation value. If the coagulation value is more, means the more moles, millimoles of a particular electrolyte is required, that means its coagulation value is more, and that is what we have. Minimum concentration of an electrolyte, suppose there are two electrolytes and suppose 5 millimoles of one electrolyte is required. I am giving you just good example, and 10 millimoles of another electrolyte is required. So electrolyte which uh, coagulates the colloid when its concentration is still millimole per liter is having higher coagulation value, but its coagulation power is less because we need to use more, and we need to use more amount or larger amount of this electrolyte for the coagulation of that sol. So its coagulation power is less, but the coagulation value is more. So the coagulation power is proportional to by proportional to 1 divided by coagulation value, means it is inversely proportional to coagulation value. Let us see some examples in this table, and we will focus mostly on the ions containing certain charge. So about coagulation of negatively charged salt, this arsenic sulfide is required. So we see aluminium AlCl3 as an electrolyte which contains aluminium 3 plus ion. So the cations will be causing the coagulation of this salt because it is an ionic salt. So cations aluminium 3 plus ion, and its valency is 3 plus. There are two other cations with two positive charge, barium cation BaCl2 and MgCl2 2 plus ion, and the other cat as well, NaCl, KCl, HCl. They also contains cations Na plus, K plus, and H plus respectively. So what do we see? The coagulation value of these electrolytes that follow this order. We need more amount of NaCl or KCl or HCl for the coagulation of the salt. Then a lesser amount of MgCl2 or BaCl2 is required for the coagulation of this AS2S3. So the coagulation value of this MgCl2 and BaCl2 is lesser than that of the monocationic electrolytes. Monocationic means the electrolyte containing cation with one positive charge, having +1 charge. That is what I mean. And this is the aluminum chloride, and we see this is even the smaller number, a smaller millimoles of this LCl3 is required for the coagulation of this AS2 H3 salt. And so the coagulation power of this AlCl3 is highest, then of these two, and then the list is for these three. For coagulation of positively charged salts, for example, FeOH thrice, if you look at, so here also we look at the valency of different anions. So this is positively charged, so we will look at the valency of anions. And this anion is ferrocyanide. This is ferricyanide. So this is actually ferricyanide. It has three charges. You can see this is ferricyanide. It means FeCN6, three negative charge. That is why those three negative charges are balanced by three potassium ions. So three charge, and then in that case the oxidation state of iron will be +3. So it is ferricyanide. Ferricyanide. So see these three negative charges shown here. The amount of this electrolyte required for the coagulation of this salt is least in all among all these examples, because it contains its valency is 3. And if you look at the potassium this is potassium oxalate and potassium sulfate. This is K2C2O4, this is oxalate ion, and this K2SO4, this oxalate ion and sulfate ion both carry two negative charge, and so a lesser amount of these two electrolytes is a larger amount of these two electrolytes is required than the amount that which is required for the means than the amount of CN63 minus ion. So the larger amount of these two electrolytes is required, and a further larger amount of these electrolytes are required, which contain anions having one negative charge, so -1 charge. So this is you can see that this is the millimoles of this electrolytes that is required for the coagulation of FeOH thrice salt, means ferric hydroxide salt, in 2 hours. And so the coagulation power of this electrolyte, potassium ferricyanide, will be highest among all these examples. Then will come these two electrolytes having valencies of the anions 2 minus, and this then will come this electrolytes with having valency of anions -1. Or means the valency usually we don't show charge. I'm just saying you to make you understand. So this is valency is 3, 2, and 1. So highest valency, so coagulation power is maximum. So the coagulation value is least. Then this comes, then this one. Let us now see coagulation of lyophilic salts. So lyophilic salts we have seen. So what are the methods that one can use for the coagulation of lyophilic salts? The first example, let us first understand the factors which are responsible for the stability of lyophilic salts. And usually what we know, lyophilic salts are very stable, and so these two properties are responsible for the stability of the lyophilic salts. So first is the charge on the colloidal particles, and we also know the size of the colloidal particles in lyophilic salts are smaller than the size of colloidal particles in lyophobic salts. And then the second one is the solvation of colloidal particles. And since we know the colloidal particles in lyophilic salts has greater affinities with the solvent or the dispersion medium, because they are because of that itself these colloids are called lyophilic salts, because they have greater affinity they have with the liquid or the solvent. These two factors are mostly responsible for the stability of the lyophilic salts. So when these two factors are neutralized by any means, a lyophilic salt can be coagulated. And so how one can neutralize these two factors? This can be done by adding an electrolyte and by adding a suitable solvent. And a suitable solvent, suppose in a particular solvent, if the colloidal particles is having affinity, it is having greater affinity. So if you add another solution or another solvent in which which is having very less affinity with the colloidal particles. So this will involve precipitation of the colloidal particles. For instance, when solvents such as alcohol and acetone are added to hydrophilic salts, hydrophilic salts means the salts having affinity with water. The lyophilic means any solvent that we tell, and the hydrophilic means salts having affinities, greater affinity with water. Water is a very polar solvent. The electric constant is around 78. That's what we know. So if you add less polar solvent like alcohol and acetone in this lyophilic salts, the dehydration of dispersed phase occurs. So water that is there at the surfaces of the dispersed phase water molecules, they will be dried up, and that is what is called dehydration of the dispersed phase occur. And once the dehydration of the dispersed phase occur, even by addition of a small quantity or small amount of electrolyte can cause the coagulation of lyophilic salt, means the hydrophilic salt in this case. So these are the two things that we do for the coagulation of the hydrophilic salt. We add certain electrolyte and we also add a suitable solvent, which depends on the nature of the uh, colloidal particles. If the colloidal particle is having affinities with water, so you add less polar solvent so that its affinity with water decreases. And this less polar solvent, less polar solvent means, and at the two having hydrogen bonding capacity, the acetone and alcohol, they will form hydrogen bonding with water molecules that dry up the this colloidal particles. And so what happens even later on, by adding a small amount of the electrolyte, one can cause the coagulation of this hydrophilic salt. Let us now study about protecting colloids and gold numbers. Protecting colloids are usually lyophilic colloids, and what this is what we are going to study, and that the gold number will is a kind of measure of the capacity of the protecting colloids, the protection capacity of the protecting colloid. So lyophilic salts are more stable than lyophobic salts. This is what we already know. We have seen it many times. Since lyophilic colloids are extensively solvated, and the reason for this is extensive solvation of lyophilic colloids. That is, colloidal particles are covered by a sheath of the liquid in which they are dispersed. So the sheath of liquid is already the liquid covers the colloidal particles in which this is already there. So because of that, the colloidal particles are more, means lyophilic colloids are more stable, and we also know that the particle size in the of the lyophilic colloids are less smaller than the lyophobic colloids. So lyophilic colloids have the unique property of protecting lyophobic colloids. So lyophilic colloids can protect lyophobic colloids. So protect lyophobic colloids means it can protect lyophobic colloids from coagulation. So when a lyophilic salt is added to the lyophobic salt, the lyophilic particles form a layer around lyophilic particles, and thus it protects the latter from electrolytes. Means the lyophil when the lyophilic salt is added to the lyophobic salt, this lyophilic salt forms a layer, protecting layer around the lyophobic salt, and this protecting layer means that these are a smaller colloidal particles. Lyophilic salts are smaller colloidal particles. They carry a certain charge molecules, and so they cover this lyophobic colloidal particles in this way. You can see these are the lyophilic colloids, smaller particles. They will also carry certain charge, and this is also having certain charge. So what happens once this charge and this charge, to neutralize this charge, um, we need more amount of electrolytes. So there are many charged particles of the same kind, and so we need more amount of electrolytes for the coagulation of this. That is what is called the coagulation, or this is called the protecting ability of the lyophilic salt. So shielding a lyophobic salt from being coagulated or precipitated on the addition of an electrolyte using a lyophilic colloid is called protection, and the lyophilic colloid used for this purpose for the protection of the lyophobic salt from coagulation is called protective colloid. So the lyophilic salt here is called protective colloid, and and this protective colloids protects lyophobic colloids from coagulation. For example, adding gelatin, which is a lyophilic colloid, to a gold salt, which is a lyophobic salt, protects the gold salt from being coagulated with the addition of sodium chloride solution. So in the gold salt, which is a lyophilic colloid, if we add a small amount of gelatin, which is a lyophilic colloid, this gelatin prevents the coagulation of the gold salt on addition of sodium chloride. And this prevents means it protects gold salt from being coagulated, and that means there is here the gelatin, which is a lyophilic colloid, is called protective colloid. Let us now see the gold number. Gold number of a protective colloid is its minimum amount in milligram that is sufficient to prevent the coagulation of 10 ml of gold salt with the addition of 1 ml of 10% NaCl solution. So what we see is the gold number is the property of protective colloid, and the protective colloid is the lyophilic colloid. This is what we know. And the minimum amount of the lyophilic colloid, and that minimum amount that 2 into the in milligrams, unit of milligrams, which is enough to prevent the coagulation of 10 ml gold salt. So 10 ml of a gold salt with the addition of 1 ml of 10% NaCl solution. And this is called the gold number. So if you add 1 ml 10% NaCl solution, and if you use a minimum amount of a particular lyophilic colloid, which can prevent coagulation of the gold salt by the addition of this solution, and that minimum amount is of the protective colloid of the lyophilic colloid is called gold number. So this gold number is properties of different. So this value depends on the different type of lyophilic salts. So it is to be noted that the smaller the value of gold number, the greater is the protective power of the protective colloid. That is what we know. If you require very small amount of the lyophilic salt to stop the coagulation of a gold salt with the addition of 1 ml of 10% NaCl solution, it means the protective power of this colloid is more, because you require only a smaller amount. If you need larger amount, it means the gold, gold number is large, and gold number is large means the protecting power of that colloid is less. Let us now see about emulsions. So emulsions we have already seen earlier. In emulsions, the disperse phase and dispersion medium both are liquids, and so this so emulsions are liquid-liquid colloidal systems, that is dispersion of a finally divided droplets in another liquid. So droplets, finally divided droplets means the droplets of one liquid in another liquid is called emulsion. So if a mixture of two immiscible or partially miscible liquids is shaken, so these liquids should be immiscible or partial miscible. If it is their solution, their mixture is shaken, a coarse dispersion of one liquid in other is obtained, which is called emulsion. The coarse dispersion means the larger particle size is there. Generally, water is taken as one of the two liquids. So, in the two liquids that we see, when we form emulsions, we consider one of the liquid as water, and so based on that, one can have two different types of emulsions. So, oil in water. And what we know, oils do not get dissolved in water, they are immiscible with water or very partially miscible with water. So when oil is mixed in water, and when the oil acts as a dispersed phase, and so why this then we called OW type of emulsion. It means oil dispersed in water, OW type emulsion, and the second type is water dispersed in oil. Another case, one can disperse water into the oil, and that is called WO type of emulsion. So OW type emulsion, WO type emulsion. This is oil dispersed in water, and that means the dispersed phase is oil and dispersion medium is water. In another, this one, water is dispersed phase and oil is dispersion medium. And the dispersed phase and dispersion medium, how do we know? If the oil is smaller in amount and water is larger in amount, means the oil is the dispersed phase. If water is smaller in amount and oil is larger in amount, then this is called WO type the colloid. So water will become dispersed phase and this oil will become dispersion medium. As you can see in this figure, oil in water. So this is water, all the blue things are water, and some oil droplets you can see in yellow color. And so the water is larger in amount and some droplets are here and there are oil, and so this is oil in water type emulsion, and another water in oil type. Water is smaller in amount, shown with the blue color. These are colloidal particles, and so this one is oil with the yellow color is the dispersion medium, which is larger in amount. So in OW type system, water acts as dispersion medium, and the example is OW. This means W is dispersion medium, is for and means O is means oil. O represents it's oil, and W denotes water. So oil is dispersed phase, water is dispersed medium, and the example is milk, vanishing cream, etc. In milk, what we know that milk is an emulsion, and in milk, liquid fats are dispersed in water. So liquid fats are dispersed in water in milk. So liquid fats are what? Dispersed phase, which is oil in nature, and the water is dispersion medium. And vanishing cream means what? It's a cosmetic cream which is used for softening and cleaning the skin. The vanishing cream. In WO type system means water dispersed in oil. Oil acts as dispersion medium, and example is butter and cream. And these things we already know, butter and cream we know, you might have seen. Emulsions of oil in water are unstable, and sometimes they separate into two layers on a standing, and this you might have seen in milk. If you keep a milk for a larger duration, you will see some of the but thick cream will get deposited at the surface of the milk, and this thick cream it means this gets the oil gets separated in that case. So emulsion of oil in water are unstable, they are not but that is stable, and sometimes they separate into two layers on a standing, and this a third component called emulsifying agent is usually required to stabilize an emulsion, and the casein protein in milk is the emulsifying agent. And so the we need emulsifying agent, which is third component, because two components we have already seen, dispersed phase and dispersion medium, and dispersed phase dispersion medium. So a third component is often required, which is called emulsifying agent to stabilize the emulsion. The emulsifying agent forms an interfacial film between the particles of dispersed phase and the medium, and because it forms a film between dispersed phase and dispersion medium, and this emulsifying agent has affinity, certain portion of this has affinity with the dispersion medium, and certain portion of it has this affinity, greater affinity with the dispersed phase, and so it will come on the surface of dispersed phase and dispersion medium, and it will mix with both of them and make them stable, make the emulsion stable. The principal emulsifying agents of oil dispersed in water emulsions are protein, and in the case of milk, as I have said, casein protein, gums, natural and synthetic soaps, etc. And for water dispersed in oil, the emulsifying agents are heavy metal salts of fatty acid, so some salts of fatty acid, long chain alcohols, lamp black, etc. Lamp black is what? It's lamp black is a black pigment made from soot, so it's a black pigment which is made from soot. So the lamp black, long chain alcohols, heavy metal salts of fatty acids are emulsifying agents for WO type system, is water dispersed in oil type of the system. Emulsion can be diluted with any amount of the dispersion medium. And for example, if you take the example of milk, what we know, you can add any amount of water. Water is the dispersion medium in this case, and the fat that the ghee is there in the form of the oil in milk. And so you can add any amount of dispersion medium. However, if the dispersed phase liquid is mixed, it forms a separate layer. So if you add ghee or oil in milk, you will see it will come on the surface. So it will form a different layer, a separate layer. However, if you add water, means that you add dispersed phase forms a different layer in emulsion. But if you add dispersion medium, it will mix completely with the emulsion. So you will not see the complete mixing of this occurs, and that thing we have seen in the case of milk. The droplets in emulsion are often negatively charged and can be precipitated by electrolytes. They also show Brownian movements and Tyndall effects because they are emulsion. Emulsions can, so they'll show the properties they will of the colloids. So emulsions are what? They are colloidal particles. So all the properties of colloidal particles will be there for the emulsions as well. Emulsion can be broken into constituent liquids by heating, freezing, centrifuging, etc. And this is what we know, emulsion broken into constituent liquids. So if you just put milk into the freezer, you will see the dispersed phase and dispersal medium will form a layer and the cream will come on the surface, or by centrifuging as well. And the centrifuging, these kind of things we see usually we use in churning of the curd to separate out the butter, or by heating as well. And by heating as well it gets out. So in by heating, what happens, the dispersion medium water will be evaporated and it will be separated out. In the case of the butter we have seen, or many most of the people have seen. So let us see colloid around us. Most of the substances we encounter in our life are colloids, and some of noteworthy examples of colloids are the blue color of the sky. The blue color of the sky is because of the dust particles and water suspended in air. And the dust particles and water that is suspended, the aerosol sol particles, which are colloidal particles, which are there in air, they scatter blue light. And since they scatter blue light, we see the sky looks blue in the color. It appears blue into the color because this reaches to our eyes. So dust particles and water suspended in air scatter blue light that reaches our eyes, and the sky looks blue to us. Fog, mist, and rain, these are also colloidal particles. So when a large mass of air containing dust particles is pulled below its dew point, the moisture from the air condenses on the surface of these particles, forming fine droplets. And this is the mechanism for the formation of fog or mist. These droplets, being colloidal in nature, continue to float in air in the form of mist or fog. And this is how the mist and fog are formed. Clouds are aerosols having tiny droplets of water suspended in air. The tiny droplet of water, if it is suspended in air, is called this is um, colloid, and this is aerosol. And these are solid aerosols, because on the dust particles water is deposited. The dust particle is also there. So on account of condensation in the upper atmosphere, the colloidal droplets of water, that means the clouds, grow bigger and bigger in size till they come down in the form of rain. So upper atmosphere, these droplets, they come and settle down, they become bigger and bigger because of the condensation in the upper atmosphere where temperature is lower. And sometimes rainfall occurs when two oppositely charged cloud meets. So if the two clouds are there which are having their all colloidal particles, they all carry different nature of charges. Suppose one cloud contains positively charged colloidal particles, another contains negatively charged colloidal particles. When they meet each other, the rainfall will occur. A rainfall will occur because once they meet these colloidal particles of different charges, they will neutralize each other, and larger size of colloidal particles will form, and that will result into the precipitation. Artificial rain can be caused by throwing electrified sand or spraying a shawl carrying charge opposite to the one on clouds from an aeroplane. So if you know the charge on the clouds, and suppose a cloud that in the particular region contains negatively charged colloidal particles, then what you can do, you can add some shawl which carry negatively. So if the cloud contains positively charged, and shawl which we are spraying through the aeroplane, if it contains negatively charged particles, so it will cause the artificial rain. So the artificial rain, if the cloud contains negatively charged particles, then we have to add salt containing positively charged particles, and then the artificial rain can also occur. So the food articles, and in the food articles, some food articles are also colloidal in nature. The example is milk, butter, halwa, ice cream, fruit juices, etc. And this milk, butter, etc. That ice creams we already know. Fruit juices, halwa, they are all colloidal. Juices which may contain certain proteins or larger macromolecules, biomicromolecules, which will form the colloidal particles, are all colloidal in one form or the other. Blood is also a colloidal solution. So blood is colloidal solution of an albuminoid substance. So albuminoid substance, say so albumin protein is there. The substances like albumin, one can call albuminoid substance. So albumin protein it forms colloidal solution, and the blood is colloidal solution. And the septic action of alum or the ferric chloride solution is due to blood septic action means it causes the coagulation of the blood. So this is called a septic action. So septic action of the means it stops bleeding by coagulating blood. And so the septic action of alum and ferric chloride solution is due to blood coagulation, forming a clot that stops further bleeding. And so this is what we know. So that this action, the septic action of alum or ferric chloride is because of this, and this causes coagulation by forming clot that stops further bleeding. And so once the clot is formed, the bleeding will be stopped. The fertile soils are colloidal in nature, in which humus acts as protective colloid. On account of its colloidal nature, soil absorbs moisture and nourishing materials. So if colloid contains humus, means the colloidal, if it is colloidal in nature, it is fertile and it will absorb moisture and nourishing materials, which is used by the plants. And so the nourishing material, if it absorbs, it means that it means the soil is fertile. The formation of a delta is also because of this coagulation. We see coagulation of the colloid. So the river water is a colloidal solution of clay. The silica particles are there in the river water, and the colloidal solution of the clay river water. On the other hand, seawater contains many electrolytes, and when river meets sea, we see seawater contains many electrolytes, salty in nature taste, and so many electrolytes are there. And these electrolytes we know when come into contact, and when electrolytes are mixed with the colloidal solution, coagulation of the colloids occur. So when river water meets the seawater, the electrolytes present in seawater coagulate the colloidal solution of clay, which is there into the river water, resulting in its deposition with the delta formation. And this is what it results deposition with the delta formation. Let's now see application of colloids. Colloids are widely used in industry, and for example, electrical precipitation of the smoke. This method is very important in the current era. The electrical precipitation of the smoke, because what you know, we don't want the smoke or the dust particles come out in the atmosphere to, to pollute it. So a smoke, so certain methods are used. Electrical deposition of a smoke. So smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. in air. So carbon, arsenic compounds, dust, etc. in air is called a smoke. Before it comes out, because it has hazardous effect on the health, so we don't want a smoke to come out of the chimneys. So before it comes out from the chimney, the smoke is led through a chamber containing plates having a charge opposite to that carried by the smoke particle. So once before it comes, smoke comes out of the chimney, what we do is pass this smoke through a chamber which contains an electrode or a plate which is having very high voltage, and a high voltage as high as 30,000 volts or even more. So what is it carry very high charge, and because this charge is there, the electric position of these particles, dust particles or the particles of a smoke, that carbon, arsenic, they will take this electron, they will get neutralized, and they will get neutralized under the effect of this effect, and they will get precipitated as ash. And so the other gases, remaining gases will come out, which will be free from carbon particles or the arsenic particles and the dust particles and so on. So the particles coming into contact with these plates lost their charge and precipitate. So when these particles, colloidal particles, which are there in the smoke, when they come in contact with these plates having very high voltage, they get neutralized, and so they get deposited, they form precipitate, and they lost because they lost their charge and they get precipitated here, precipitated. As you can see, the particle the settle down on the floor of the chamber, and the precipitator is called Cottrell precipitator. This kind of precipitator is called Cottrell precipitator. Then we also use this application of colloids in purification of drinking water. The water obtained from natural sources often contains suspended impurities, and these suspended impurities are also in the form of colloids. So when you add alum to it, what happens? The alum neutralizes that colloidal particles, and so precipitate will form. So these things you might have noticed. I have noticed in my childhood, because sometimes when you add alum into the water, that is taken from the even from the mm, hand pump or any other thing. And what happens if you add alum to it? You will see some of the precipitate will come. It will get deposited on the bottom of the container, and so this is because, and this way one can actually purify the water as well, because many unusual unwanted materials will be there in to the form of colloid in water, and so they will get deposited there, and thus one can filter it out, and so water will be purified to a certain extent. Colloids are also used in medicine. Most medicines are colloidal in nature. For example, Argyrol. Argyrol is a silver salt used as an eye lotion. So Argyrol, silver salt. So salt means the silver colloidal particles are silver here. This is used in eye lotion. Colloidal antimony is used in curing kala azar. Colloidal gold is used for intramuscular injections. The colloidal golds. Colloidal medicines are most effective because they have a large surface area and are easily assimilated. So if anything is having large surface area, it will easily get assimilated, as well as its action will also be more efficient, because usually actions happens at the surface of any particle and its surface area is more, so it will be more effective. Then the use of colloids is also in the tanning, and the tanning is the animal hides, which are nothing but skin of large animals, which called animal hides. So hides are colloidal in nature. All this skin of large animals are colloidal in nature. When a hide which has positively charged particles, when these hides have positively charged colloidal particles, is soaked in tannin, which and this tannin contains negatively charged particles. The colloid will be coagulated, and these colloids, the positively charged particles of the tannin, will get precipitated, or the mutual and the coagulation of the tannin will also occur, and the hide will also occur, and the colloidal particles in hide, and because of that a mutual coagulation occurs, and which will result in the hardening of leather, and this process is called tanning. So hardening of leather by use of tannin, which contains negatively charged particles, by the mutual coagulation is called tanning. And these days chromium salts are also used in place of tannin for the tanning of leather or the animal hides. Cleansing action of soaps and detergents are also the colloidal behavior that we have seen. Micelle formation and other things in great detail we have already seen. The photographic plates and films. The application of colloids are also in photographic plates and films. Photographic plates or films are prepared by putting an emulsion of the large sensitive silver bromide in gelatin over glass plates of celluloid films. Celluloids are what? A highly flammable substance made from cellulose nitrate and camphor and used in motion picture and X-ray films. So the celluloid use has decreased. It has been decreased with the development of non-flammable thermoplastics, because it is highly flammable. So its use is now decreased, and now people use non-flammable thermoplastics in place of celluloids. And what is celluloid? Chemical nature is cellulose nitrate and camphor, and which is used in motion picture and X-ray films. Rubber industry, the latex is colloidal solution of rubber particles. So rubber particles, they form colloidal solution, which is called latex, that are negatively charged. So this latex, the colloidal particles in latex are negatively charged, and rubber is obtained by coagulation of latex, and the coagulation of latex on this what we obtain rubber. So the solution, colloidal solution of rubber is latex, and once you coagulate the latex, so the colloidal particles of latex means that are the rubber will get deposited, which we call the rubber. So industrial products are also the paints. What we know, they are colloidal in nature, solids in liquids, inks, colloidal in nature, synthetic plastics, colloidal in nature, rubber, graphite, lubricants, cements, etc. are colloidal solution. Let us now see the summary of this chapter. I'll just read it out, and we have seen a large number of things in this chapter. So at first we started with the adsorption. Adsorption is the phenomena of attracting and retaining the molecules of a substance on a solid surface, resulting in a higher concentration on the surface than in bulk is called the adsorption. So in bulk, the adsorbed particles will not go to the concentration of this particles. The adsorbed particles will be more on the surface than in bulk. This is called adsorption. The substance adsorbed is called adsorbate. So substance which get adsorbed is adsorbate, and the substance on which adsorption takes place is called adsorbent. In physisorption, and we have seen the adsorption is of two types, the physisorption and chemisorption. In physisorption, adsorbate is what? Substance that gets adsorbed is adsorbate. So adsorbate is held to the adsorbent by weak van der Waals forces, and chemisorption, a strong chemical bond holds adsorbate to adsorbent. Almost all solids adsorb gases, and this is what you should know. Almost all solid can adsorb gases. The extent of adsorption of a gas on a solid depends upon the nature of the gas, the nature of the solid, the surface area of the solid, the pressure of the gas, and the temperature of the gas. These are the factors which actually governs the extent of adsorption of a gas on the solid, and the relationship between extent of adsorption and extent of adsorption is defined by x by n, and the pressure of the gas at constant temperature is known as adsorption isotherm. So this relationship with the extent of adsorption and the pressure of the gas is known as adsorption isotherm, and this adsorption isotherm we already have seen x by m versus pressure plot. A catalyst, then we saw about the catalyst. Catalysis we have studied. So a catalyst is a substance that enhances the rate of a chemical reaction without itself getting used in the reaction, and this catalyst does this by decreasing the activation barrier of of the reaction. So the phenomena of using catalyst is known as catalysis, and this catalysis could be of two types, homogeneous and heterogeneous, and this we have seen. And what is homogeneous catalysis? If the catalyst and the reactants are in the same physical state or the same phase, the process is called homogeneous catalysis. And if the catalyst and the reacting substances are in different physical states or the different phases, the catalysis is called heterogeneous catalysis. Examples and the mechanism of heterogeneous catalysis we have already seen. I'm just summarizing it. Colloidal solutions are intermediate between two solutions and suspensions. It means their behavior usually of the properties of the colloidal solution, most of the properties it lies between the properties of true solutions and the properties of suspension. If you look at the size of the colloidal particles, size of the colloidal particles is between 1 to 1000 nanometer, and in suspensions we see the particle size is more than 1000 nanometer, and in true solution we see the particle size is less than 1 nanometer. Less than 1 nanometer in true solutions, and that we see the in middle between 1 to 1000 nanometer the size of the particles, so they are there in the colloidal solution. A colloidal system consists of two phases, the dispersed phase and the dispersion medium. And dispersed phase is what one which is in lesser amount is dispersed, defined as dispersed phase, and one which is larger in larger amount is dispersion medium. The colloidal systems are classified in three ways depending, and there are three ways of classifying colloidal solutions, and that so three ways we have seen. The physical states of based on the first is the physical state of dispersed phase and dispersion medium, and based on this we have seen different types of colloids. And then the nature of interaction between dispersed phase and dispersion medium, based on that we have seen two different types of colloids, lyophilic and lyophobic. And then the nature of particles of dispersed phase and dispersion medium, and then here we have seen three different types of colloids. The colloidal system showed interesting optical, mechanical, and electrical properties. The, this, these properties we have seen in last two classes. The process of changing the colloidal particles in a sol into insoluble precipitate. So in a sol, if the colloidal particles are there, if you want to change this into precipitate by adding some suitable electrolytes, this process is called coagulation. In the coagulation, we have already seen. Emulsions are colloidal systems in which both dispersed phase and dispersal medium are liquids, and the emulsion can be of two types: oil in water type and water in oil type. Oil in water type, OW type; oil in water type, oil in dispersed phase and water in dispersal medium. Water in oil type means water is dispersed phase and oil is dispersion medium. Examples we have just seen. The process of making an emulsion is known as emulsification, and to stabilize emulsions, we need emulsifying agents. An emulsifying agent or emulsifier, which emulsifying agents are also called emulsifiers, is added to stabilize an emulsion. Soaps and detergents are most frequently used as emulsifiers, and the most frequently used emulsifiers are soaps and detergents. Colloids find several applications in industry as well as in daily life, and these applications we have just seen in industry as well as in daily life. Now this chapter is over. I'll come with a new chapter in the next class. I hope these points are just, most of the things are just to be remembered. These are just information based. Some where some understanding is required that I have tried to explain. I hope you have enjoyed this